Welcome. This is Get Started with Essential Physics Part 2, in which we're going to focus on the hands-on investigations with sensors in SPARKvue in the Essential Physics curriculum program. Part 1, happening earlier today, was a focus on the resources, specifically the books and online resources to support everything from investigations, which is the focus of Part 2, to regular assignments, filling in absences, and other resources that are available with the book system. The focus on Part 2 is specifically on investigations, and more precisely on those investigations which are going to use sensors and the SPARKvue software. So that's the focus of Part 2. You can register for either of these sessions. They will happen in the future. We're going multiple times, August 6th through September 11th. You can register, or you can view prior recordings once they are posted at the website pasco.com/training. I'll ask Kane to perhaps put that in the chat, so you can just open up that link if you wish to register for anything coming up. Here's the agenda for our Part 2 session today. We're going to do a very quick overview of the program resources and review that. Since those are the resources that we covered in Part 1, it will be a brief overview, but the focus there is going to be just a reminder of where we're going to get the resources that will support the investigations that we'll be doing in the coming session. Then we're going to do 3 investigations. The first is an introduction to the basics of SPARKvue and the core sensor used in many of the mechanics experiments, the smart cart, and that's graphs of motion. We'll have a quick interlude to talk about the equipment kits that are available for SPARKvue, and then we'll jump into the final 2 investigations. One is a more complex data collection and analysis procedure to determine the relationship between force, mass, and acceleration, that is Newton's second law. And then we'll jump away from the smart cart and take a look at the modular circuits kit in an investigation of resistors and confirmation of Ohm's law. All right. So, quick review. What is Essential Physics? Well, the Essential Physics program has many components. Student textbook, a physical student textbook is one of them, a corresponding ebook that replicates all the content of the textbooks, plus adds interactivity. A teacher ebook with the resources for both students and teachers to be successful with Essential Physics, and then some online resources, including an infinite test bank and the PASCO Physics Academy. And it was these components in the top row that we focused on in Part 1. Adding to that for Part 2, we're going to be now talking about equipment, specifically sensors that are in the equipment kits, and the software that can collect data and allow you to analyze data from those sensors, specifically SPARKvue. We will be jumping back to some of the resources, though, because we need to figure out, well, how do we do the investigations with the kits and software? Well, we're going to use resources specifically that are in the teacher ebook resources. There are 2 ways to access these resources. The traditional way is the one we'll show in the first activity, going to our education.pasco.com site. But there's a new way. About a month ago, we opened up the PASCO portal for science education, and the teacher resources that are available in the teacher ebook and online are now also in the portal, with some advantages in the portal that I'll talk about shortly. So, a review of how to get to the books. There is a student ebook, there is a teacher ebook, and both can be accessed at our education.pasco.com site. And you would access either of those using a student or teacher access code. When you go to the site, education.pasco.com, if you've never logged in before, you're going to see some prompt like this you see on the right under our chemistry textbook that says enter access code. And if you enter either a student or teacher access code, it's then going to show you some buttons that will allow you to enter either the student book or the teacher book, and in the case of the teacher login, some additional resources such as Test Bank and Academy. This is exactly as covered in Part 1. The alternative to accessing the textbook and resources via the education.pasco.com website is to access those from the portal. Everyone who has a subscription to the portal, these are 1-year subscriptions for entire schools, for use by teachers at that school. Everyone who has a subscription to the portal gets access to our teacher ebooks without any access codes. And if your school or district has purchased the textbook for students, the portal will give you a shortcut to opening the student textbook and sharing that link with students. A little bit more about the portal. These days, many schools have constraints on the technology used by their students and teachers. They want the convenience of being able to tell students you can just log in once and access all of your resources. That's called SSO, or single sign-on. And we wanted to give access to the student textbooks via single sign-on. That's one of the features of the PASCO portal. Another feature is support for LMS, or learning management systems. Many schools are moving towards distribution of student assignments and collection of those assignments via learning management systems, including these 4 shown here. So we support that through the portal. The assets that you're going to use from Essential Physics are the same, whether you're accessing them via education.pasco.com or the PASCO portal, but the PASCO portal enables you to distribute and give student access to those resources in a different way. If you'd like some more information, you can visit pasco.com/portal. Today, I'm going to show you how to access resources both the traditional way at education.pasco.com and via the portal, so you can see a look at both of those. The portal does have some other resources, experiment library, professional learning, and things like that. But for today's discussion, it's a different way to distribute the assets, the resources for Essential Physics. Throughout the presentation, when I'm talking about something the portal way, I'll have this blue box around it, so we can distinguish that from the education.pasco.com path. And thanks, Kane, for posting that link in the chat. So a quick question, poll question. I'm curious if you access Essential Physics already, whether you access it through the education.pasco.com site or the PASCO portal. So let me launch a poll here. And this poll should pop up in a window for those of you who are joining us live. And it asks, if you have Essential Physics, do you access its resources through the education.pasco.com website or the PASCO portal? Those 2 options, or I don't know. School year is just starting for many of you in the coming weeks, so this may be something that you are learning about shortly as you talk to your administrators and science department heads. Great. So I'm going to end the poll here. It looks like the responses have slowed. And looking at the results, which you should be able to see, we can see it's an even split between education.pasco.com, PASCO portal, and I don't know. So I'm going to cover both of those today, education and PASCO portal, so you get a look whichever way you're accessing those resources. Thanks for taking the poll. All right. So central to all of these investigations is accessing the teacher resources. If you joined us for part 1, you learned that we can access it in the teacher ebook in the sidebar of investigations. And we can also access it in the chapter resources of the portal. These resources are the same, it's just the presentation that's slightly different and the different opportunities the portal provides for distributing it via Google Classroom and LMSs. Key, though, is what resources are provided for investigations. As we saw in part 1, we have lesson plans to give you, the instructor, some guidance on where this fits into the curriculum, what tools you'll need, how you can introduce it. Slides that you can present, both covering the content of the lesson in terms of the physics covered, and, as we'll see shortly, the mechanics of actually doing these investigations, from lab setup to button pushing in SPARKvue. The student work, it could be a traditional worksheet, but in the case of the lab investigations, our focus in this session, there will be a lab investigation handout that students can follow and provide places for them to write their responses on paper or in a PDF form, or one of many ways. We'll look at one of those ways today. There's a teacher key that gives you typical data and results. And then for most lab investigations, those specifically that use PASCO sensors and software, plus some others, there's a teacher video that's essentially a teacher saying, you know, that lab that you're thinking about doing, here is an overview of that lab. So you can decide, A, whether to use it. And if you do decide to do that lab, here are the key things that you as an instructor need to know. So we'll take a look at one of those teacher videos as we go through these 3 investigations today. Before we jump into these hands-on sensor-based investigations, I want to remind you of something we covered in part 1, and that is about half, perhaps the slight majority of investigations in the Essential Physics textbook are investigations that don't require PASCO sensors and SPARKvue software. These comprise investigations that are just hands-on with more traditional equipment, and many, many investigations that are simulations. So look back to part 1 for a demonstration of some of those simulations. And remember that the investigations we're focusing on today are going to be those here in part 2 that use sensors and software. All right, so let's jump into the first investigation. This is the first investigation in the book and our first investigation today. It is investigation 1A. 1 means it's in chapter 1, A means it's the first of what might be multiple investigations embedded inside the book. And this one's called Graphs of Motion. This appears on page 5 of the textbook, well before students should have any idea about graphs of motion, and long before they cover kinematics equations, but it's in there for a couple of reasons. One, to get them excited about collecting data and the technology that's integrated into essential physics. Two, to have their graph skills tested and begin to think about how real data can be analyzed in the graph. And also just a way to emphasize that this is hands-on stuff and introduce them to the core pieces of many investigations in essential physics: the smart cart, which is a rolling suite of multiple sensors, and the SPARKvue software that enables them to record and analyze data from that smart cart. So if we go to textbook page 5, I will do so here in the student textbook. So I'm logged in as a student in this browser. If I open the book, I could jump directly to page 5. And I can see that in the book itself, I get a very basic set of instructions as a student. But as you learned in part 1, there are many resources that supplement this for the performance of this particular investigation. So let's talk about those additional resources. In the teacher book, there is a student handout, and that's what I'm going to use as the basis for going through this investigation. First, we'll look through it as a student might, and then we'll take a look at how we can support them as they go through this investigation. I want to note that the student handout is not in the student book. We saw in the student book, there's no sidebar here. Just as a reminder, it's the teacher resources that include the student handout. So the teacher's in control of how and when to distribute that to students. So I'm going to go into the teacher version of the book to grab this handout so we can take a look and read it a little more clearly. I will return here to a different browser where I am logged in as a teacher. And at the education.pasco.com site, I will choose to open the book, and I could jump directly to page 5, or I could recall that there's an investigations button that on the home screen of the textbook shows me all the investigations, and I can jump directly to that page by clicking here. And it's in the teacher version that we see things like lesson plans, slide presentations, and so forth. What we're looking for right now, though, is the student work. So I'll open up the student work, and this is the handout. These are the instructions, and as you can see, the place where students can respond to questions. Some teachers choose to print these. Some teachers take the Word doc and modify it before they distribute it. Other teachers note that this is a form. So this is a PDF form that students could type into those responses that can be entered via text. So I'll do that in this particular case, but as a student, let's look at this. And remember, it's on page 5. This is before they've done anything in the book. And we need to think from the teacher's perspective. They don't really know about any of these steps. So of course I could guide them through it. But if I am also new to this is page 5 of the book after all, what resources are there available for me to help my students through this? So the resources that are in addition to the student handout include a set of slides. And I've taken some of the slides, we'll look at where they come from later, but I've taken some of the slides that are provided in the sidebar of the teacher ebook, and I've just selected them. There are many more slides than I'm going to show here, but I want to note that when you have slides for an investigation, or a lesson that includes an investigation rather, they typically include very precise instructions. So you might look at the student handout here and say, wait, they don't know where to open this. They don't know how to connect the sensor wirelessly. But our student instructions are intentionally concise because they're going to learn this. So if we included the very verbose instructions every time, that's just wasted paper and wasted space. So with each lab, it's kind of up to you to determine what level of detail you'd like to provide. And much of the time, the detail is provided here in the slide. So let's imagine we're the teacher and the student says, wait, how do we open that file? How do we connect the sensor? Well, there's a slide that you can project to show that. And as we go through, you'll see there are slides for each of these new to us steps in SPARKvue. So let's begin by opening an experiment file, powering on the smart cart, and connecting it to our software, knowing that we're guided by these slides. So I'll turn on the video here, and you can see that I have a smart cart. So we need to open the experiment file. The software we're using today is SPARKvue. I'll provide a lot more details on SPARKvue as you go, but for now I'm going to launch it, and we'll see that SPARKvue opens to what we call the welcome screen. There are a number of paths that you can take inside SPARKvue depending on your goals, but it is the case that for 100% of the essential physics investigations that use SPARKvue, you will always start in the Open PASCO experiment button. So I'm going to do that here. And I'm asked as a student to open the file 01A graphs of motion. And if I look at the experiments that are built into SPARKvue, I see that there is a folder of essential physics files. And the first one there, 01A, is exactly what I'm looking for. I'll open that up. And all of these files are going to provide a configured set of displays, sample rates, and all the things that need to be set up for student success in collecting and analyzing the data so that your students are not spending time configuring the software, rather they're getting to data collection and analysis as quickly as possible. So the next instruction after we open the file is to power on the smart cart. So let's talk about that. The smart cart is one of our wireless sensors. Most of our wireless sensors are white, but in the case of the smart cart, we very intentionally have a blue one and a red one, so we can do things like collisions and talk about the blue cart, the red cart did this. But all of our wireless sensors, whether a smart cart or otherwise, have a power button on them because they have a built-in battery. I'll turn the power on to the smart cart, and all of our wireless sensors have a Bluetooth icon next to an LED. And when that Bluetooth button, when the Bluetooth LED is blinking red, that means that we are now able to connect this smart cart to SPARKvue software running on some computer. So how do we do that? Well, the slide, again, a resource that teachers can use to help their students, tells us that we're going to hit that Bluetooth button to open the wireless devices dialog and find our smart cart. So I'm going to click on the Bluetooth icon here. And what's going to happen is SPARKvue is going to go out and look for devices that are PASCO sensors that have a wireless measurement on them. And just to show you what a classroom might look like, I'm going to give Kane another smart cart. This happens to be a red one. And Kane's maybe about 3 meters away from me, maybe a typical lab distance away. So one of the things we face in the classroom is we may have multiple sensors of the same type. First thing you may note here is that SPARKvue tells us that these are the PASCO sensors within range. Typical range is about classroom size. And we need to figure out which of these smart carts is mine and which is Kane's. Well, as you can see from the video, mine happens to be blue, and SPARKvue can tell what color the cart is from its ID information. So I know that mine's blue and Kane's is red, so mine is definitely not the red one. I can confirm that a couple of ways, though. Another thing to know is that the wireless sensors typically populate in this list from the strongest signal at the top to the weakest signal down below. So I can see the blue smart cart is very close to my computer. It's at the top of the list. Kane's red smart cart is a few meters away. It's lower on the list. And these other PASCO sensors that we could potentially connect to for other experiments are probably in the room next door. The definitive way to determine, is this my smart cart in the list, is to look at the case of your smart cart. And it will have next to the Bluetooth light a 6-digit ID. My physical smart cart has the label 015-026, and I can see that that indeed matches the blue smart cart that I see here, 015026. We can see that our smart carts are close enough together that they're now kind of jumping back and forth in terms of the closer one. But I know that this is mine definitively from the 6-digit ID. So I'm going to click on my smart cart in this list, and SPARKvue is going to connect to it via Bluetooth. The version of Bluetooth that our wireless sensors use is Bluetooth Low Energy. And the real beauty of Bluetooth Low Energy is that we don't need to go into our operating system settings. The connection procedure happens inside the SPARKvue app and happens the same across all devices, whether it's Windows, Mac, iOS. We'll talk about those different devices in a bit. My cart is now connected, and I can tell that two ways. One is it's moved up into the connected devices portion of the wireless devices list. The other is that the Bluetooth light is now blinking green instead of red. That means it's been connected. All right, I only need to connect my smart cart, so I'll go ahead and hit done. By the way, my smart cart becomes unavailable to Kane once it's connected because a sensor can only be connected to one computing device at a time. But if I wanted to do a collision or something, I could connect to the red smart cart as well and have both the blue and red. So you can have multiple sensors, but a sensor can be connected only to one instance of SPARKvue at a time. Now that we've connected our sensor, we can see that we have plots of position versus time and velocity versus time. So let's return to those student instructions, and it says, start data collection and move the smart cart back and forth on the table. Well, there's a slide that helps us to learn that collecting data is a matter of simply hitting the start button here at the bottom. So I'm going to hit the start button and then simply by hand move the cart back and forth, and let's see what happens to our graph. So left, right, I can stop for a bit and move it however I'd like. Fast motion, slow motion. And this particular file is configured to stop after 10 seconds. So I don't need to hit the stop button. You may have noticed that the start button turns red into the stop button after I begin collecting data, but this file automatically stops after 10 seconds. So let me show you one thing that I would add to this slide. All of the slides are editable. So I would add a slide that says, my students, you're new to SPARKvue. I want you to know the most important button here in the graph toolbar. The graph toolbar is this down here, and you can open it up and a tray of tools open. And the leftmost button, if I hover over it, is scale to fit. That's going to take whatever scaling your graph has, look at the data, and when you press the button, it's going to automatically change the axes and move the graph around so that your data is filling the screen, making it easier to interpret. So the scale to fit button is one that will allow us to get the best view of the data. And you can press scale to fit while you're collecting data. You can also press it after data collection, as I did just here. So we've seen how the position velocity graphs of the smart cart change as I move it. Position here at the top, velocity in the lower plot area. Now there are a series of questions in this handout that ask us as students to do a couple of things. First, push the smart cart across the floor. I happen to have it on the tabletop here, but let me do that and we'll let go and see what happens to velocity. All right, so I'll hit start and then I'll push the cart to your right. All right. And here's velocity at the bottom. So we can see that it kind of went down and went back up. I kind of have a little tabletop here that's bowed. So let me do it a little more slowly and we'll see what else happens. All right, that probably is more what they're going for. So here on the bottom, we have velocity from me just pushing it to the right from our view. And we have velocity initially it went up and then it gradually trailed off until it went to close to 0. And I'm using the PDF version of this handout. So this is actually a form. And if I wanted my students to respond electronically, they could just answer directly in this form within most PDF readers. So I could say the velocity gradually decreased. And what causes this? And they might think friction, they might think table is at an angle, something else, but you can see that they can type their responses directly in this document with the instructions. So now that we know how that form looks, let's just quickly jump to some of the other trials we're asked to look at. If you roll the smart cart down a ramp, well, I have this on a board that I can actually lift. So I'm going to lift the left side from your view of this board. And when we return to SPARKvue, let's collect another run of data that shows the smart cart going down a slope. So I've lifted this end, the cart's a little higher, closer to the camera. Hit start. There we go. So that's down the ramp. And in this case, we can see the velocity increased fairly steadily instead of decreasing gradually in the first flat trial. And as you can see, this isn't an interpretation of how motion works, but it is an opportunity for students to start to hone their skills at interpreting what a graph of something looks like and how it changes over time. Let's do one more thing. Try to move the smart cart across the table with constant velocity. What's the shape of the position time and velocity time in that case? So returning to SPARKvue, another run. By the way, each of these times I press start and then stop, we're getting what's called a run of data, and all the runs of data are being shown here in the graph legend. You may be saying, wait, what happened to that prior run? Well, there's a visibility checkbox, and by default, SPARKvue hides prior runs, but you can always make them visible again by just checking on them. So here, run number 3, this one here in green in the velocity time plot, that's the flat, and then the down a slope is the brown one. So we can always make prior runs visible if we want to make a comparison. So this time it's me trying to push the cart at constant velocity, so I'll press start. And it's a bit of a challenge, but I tried to go fairly constant here. And if we look and compare to the prior ones, we can see that I somewhat achieved it, but it didn't decrease consistently or increase consistently when I tried to push it at constant velocity. There's one more challenge here, and that is try to determine how the smart cart actually tracks its motion by rolling each wheel by hand. So I'm going to go back to SPARKvue and show you when I press start. I'm going to roll this wheel right here. I don't see anything. It turns out these two wheels are connected. And if I roll this wheel, there. So it looks like this pair of wheels near this end of the cart, this happens to be the force sensor, it looks like the sensor is measuring the rolling of these wheels toward the front of the cart. Why front? Well, we didn't talk about it, but you'll notice that there's a big plus X printed on the top of the cart. And if we go back and look at our prior measurements, when I was moving the cart to the right, its plus X direction, I had a positive velocity, and we could, of course, begin to explore what happens the other direction, which is part 2 of this lab. First, though, it's asking us what is the minimum position, the smallest distance the smart cart can record now that we know it's measuring the rolling of its wheels. Well, we can scale to fit, as we learned earlier, but we can also manually scale, as this slide helps us to learn. We can drag the numbers on the Y or X axes to zoom in. I'm going to drag on the numbers here and try to figure out how small are the smallest jumps. I can also pan, by the way, so I'm going to pan this way. And I want to see what are the smallest jumps between position data points. Looks like these and these are fairly small. So I could really zoom in and try to determine that. It looks like, so 0.0070, that's about that point, and 6.8. So that seems to be, what, 0.0002 meters, or 2.2 millimeters between them. We'll learn later there are graph analysis tools, and one of the most useful is this coordinates tool. So if I wanted to actually determine what are the real coordinates of that without having to read the graph axes myself, I could turn on coordinates tool and see that that indeed is 0.0070 meters. And I could jump to the left and see that is about 0.002 meters away. All right. So that's a quick quick introduction. I do want to show you that there is a part 2 of this investigation. We're not going to do it completely, but I want to show you something important, and that is this SPARKvue file we opened that has the displays already configured can have different pages with different sets of displays as appropriate for different parts of the experiment. So the instructions ask me to move forward to part 2, where we can see all the prior runs. I know I could hide these, but they are going to go away when I do the next run. This part of the lab is a graph matching challenge, and it's basically asking students, now that you know what a position time graph looks like when you're rolling the cart, how would you have to move the cart to create a graph that looks like this or like this? And this is a very popular activity for graph interpretation skills, and it's nice kinesthetic activity. If I wanted something like this, so it looks like the position's constant, and then it goes up, it must be to the right, and then it's constant, and then it goes down. And we can interpret it verbally like this if we have those skills, or we can just play around with it. I can go and say, you know what? Well, it's flat when I don't move it. If I move it left, it's negative, so that's not what I want. Let me try again. I'm going to move it stationary, move it to the right, wait, move it to the left, wait. I think I'm onto something now. That looks like what is being requested in this graph matching activity. All right. So that is a quick introduction, most crucially, to connecting sensors to SPARKvue software and collecting data and doing some analysis, all in the context of students can be following along the instructions on their handout, responding there if that's how you wish for them to respond, and all of this is supported with resources like the slides that I am using to show the details of how these steps can be done inside SPARKvue. Ken, any questions about the lab so far?
Not about the lab.
Okay.
There's a question about iPads.
All right, great. So we've seen a couple of the resources. I want to kind of summarize the resources that are available. We haven't looked at all of them, but this is true across all of the investigations. We have the student textbook or ebook, which has the basic instructions. So this is a great way for students to get a preview of the lab before they actually do it. You could ask them to read this kind of as a pre-lab assignment because it's in their textbook before you go into the teacher ebook yourself and do things like download the lesson plan to view the lesson plan and make a plan for doing this investigation with your students, adjusting it as appropriate to their needs. You can watch a video. So I'm going to open up this video in a moment, but for all of the investigations that use sensors and SPARKvue software, there is a video that can guide you, the teacher, through this. One of my colleagues describes it as you're running late and that teacher who you know did this lab last year, they give you 5 minutes of their time and tell you this is what you need to know. So let's jump over to the teacher ebook and see where we can get some of these things. Again, they're all in one spot. So if we go here to the teacher ebook, I'll open up the ebook and we are again investigation 1A. So we have the lesson plan. We have the video. So I'm just going to play some sections of this video to get the tone of it.
What do graphs of motion look like? This is the question that students will explore in Investigation 1A, Graphs of Motion. The primary goal of Investigation 1A is to introduce your students to data collection and graphing using the SmartCart and SPARKvue software.
All right. And he goes on to talk about the context of this. It's not really about motion, it's about graph skills. And then he doesn't do the complete lab, but he says, here's part one.
Investigation focuses on collecting real-time data that represents the motion of the cart. Students begin by opening the SPARKvue experiment file indicated in their student handout.
So these are the same steps that are shown in the slides. Where do you get the file? And although not all the data is collected in these videos, all the key steps about how to open the file, especially in the early videos, how to connect the sensor, and then how to do the analysis are covered. So he walks through the connection, collecting a run of data, and there are sections of video for part one, part two, which is the matching portion.
Before recording data in part two, students should go to the second page of the SPARKvue experiment file and then hide all the data so the graph is blank.
And then moves on to part three, which we won't do now, but introduces the idea of exerting a force on this cart to make it move. So whenever I need a reminder of what this lab does, if I've never done it, or need to get the gist of the lab to determine if I want to do it, or want someone to tell me what the key points of it are, I always look at these videos that are accompanying every investigation that uses sensors and SPARKvue software. So that's another great resource. There's also the slides. They are longer than just the slides I showed you, but in the context of investigations, we saw that the real key here is that there are very explicit instructions that aren't included in the student handout, but are included in the slide set. We saw the student version of the handout, and then the teacher ebook also includes a key for that. So just to emphasize something you've probably already inferred, remember that even the student handout is not in the student textbook. All of these resources, whether something the teacher themselves will be using or will be distributing to students, are provided as a sidebar in the teacher ebook or in the portal. And we'll look at the portal as a way to access those in the second activity. All right. So a little bit about equipment kits, if we don't have questions about the investigation. Looks like we're good. So we currently sell 2 equipment kits for Essential Physics. The core standard kit includes basically 2 core sets of sensors. One is for mechanics, and that's centered around the SmartCart. We have red SmartCart, we have blue SmartCart. They are identical except for color. And you get a lot of accessories for doing investigations in mechanics with the standard kit. The other cluster of components is a series of sensors that include a current sensor, a voltage sensor, and magnetic field sensor, all centered around our modular circuits kit. And it's this modular circuits kit that we'll look at in the third investigation today. We also have a larger bundle that allows you to do even more hands-on investigation with PASCO sensors. It includes all of the same modular circuits and mechanics equipment, some additional mechanics equipment, including a second SmartCart to enable things like conservation momentum collisions, some 2-dimensional investigation components like the photogate, or the wireless smart gate, a projectile launcher, and some other things for doing pendulum and other experiments. Then there are some components that can help you with waves and sound, like the sound sensor, resonance tube, tuning forks, and then a cluster that includes optics. So these are the standard and comprehensive kits. Let us know if you have any questions about them. If you do want to know more details about the components, you can simply go to the education.pasco.com site. And if you scroll down past the place where we log into the textbooks, you will see that there are links to the details for both of these kits. Essential Physics has been out for quite a few years now, and there are adopters who may be attending today who adopted 5-7 years ago. So I want to note that we have had previous iterations of the equipment kits. The primary differences here were different types of stands, slightly different configurations of sensors. But we still completely support this kit. Sometimes that support requires that we have 2 slightly different sets of instructions. So for some investigations, you're going to see that there's a picture or a label that says equipment A looks like this, equipment B looks like this, and there will be different files provided for you to share with your students or use yourself based on which equipment kit you have. One example would be if you look in the sidebar of a Newton's second law experiment that we're going to do shortly, you will see that there are specific student work and answer files for equipment set A, the older equipment kit, or the current equipment kit B. All right, so we've talked briefly about equipment. The next thing we have to cover is where did that SPARKvue software come from and on what platforms will it be supported? I've seen some questions in the chat there that Kane is answering about iPads. So I happen to be using a Windows computer, but our goal with SPARKvue is for it to operate across all the platforms that you might possibly have in your classroom and to operate as similarly as possible across all those platforms. So let's start with what might be in the US the most popular education platform, at least in the K-12 market these days, and that is Chromebooks. The Chrome web store holds the free SPARKvue application, so it can be installed there. If you or your students have installation rights, they can get it there. Otherwise, your IT folks can push out the free SPARKvue application to the Chromebooks in your school. SPARKvue is also a free app available in the Apple App Store for iPhones and iPads. And if you have Android phones or tablets, it's available as a free app in the Google Play Store. Now, it's also available for Windows and Mac, but the situation is a little different here. Here, you need a licensed installer. It's not a free app for Windows and Mac, but the good news is that if you have a license for the book, you will get the software free, or if you have the portal, you get it free. So you can find the licensed installer on the education.pasco.com website as long as you have logged in there with ebook access. So I can access the ebook. That means if I scroll down, I can see and download the full license for SPARKvue on Windows or on Macintosh. And for convenience, it provides the link to the mobile apps here. By the way, if your students log in with the student login, they will also be able to access the Windows and Mac installers. That may be great for their own computers. It probably doesn't work for managed school computers, but it is available to them if appropriate. Now, recently there's been SPARKvue is also available on our handheld data loggers like the Spark LXi2. Recently there's been a big development that we're really delighted about, and that is the fact that we can run SPARKvue as an application, a standard application that gets installed on our devices, but we can now run SPARKvue as what's called a progressive web app in a web browser. So some schools have difficulty, or some teachers, I should say, have difficulty getting things installed. Some changes will be in the future here in the way that apps get distributed. For those situations, or if you just prefer to have a quick way to get to SPARKvue, we have what's called SPARKvue Progressive Web App that runs in the browser, and I'll give you some more details here about that. We're going to contrast the SPARKvue application for all these platforms to the SPARKvue PWA, I'll call it. This simply stands for Progressive Web App. This is a way for a fully featured application to run in a browser. What really amazes me is that our software developers have made this work in a browser, and of course, more and more things work in browsers these days, but it works with all of our hardware. So in the next activity, we're going to collect data from the smart cart directly into our browser. SPARKvue is pretty much going to look and act the same, except for one important exception, which we'll cover. And it doesn't matter whether I would do this next investigation with the SPARKvue application that's been installed or the SPARKvue Progressive Web App running in my browser. What do you need to know about the Progressive Web App? Well, it's completely free. It runs in the browser. It does have particular requirements for the browser and platform, though. It runs in either the Chrome, that's the Google Chrome browser, or the Microsoft Edge browser. By the way, both these browsers are available on Mac and Windows, even if it's a Mac computer. So you need either the Chrome browser or the Edge browser because they support these PWA frameworks. And you have to be running it on Windows, Mac OS, or Chrome OS. And it is free. It's free because all you need to do is go to a website. So you may think this is the website for learning more about this. It is not. It is the website for actually running SPARKvue in the browser. So if you're interested in doing that, Kane has kindly put that link in the chat. When you launch it, it's going to open up SPARKvue and you're going to be on the welcome screen as soon as it's downloaded. I'll demonstrate that in our next activity. All right, let us know if you have any questions about the PWA. If not, we're going to jump to the next investigation number 2 in our series, and this is Newton's second law. We are once again going to use the smart cart, but this time there's quite a bit more data analysis in this process to discover the relationship. How is an object's acceleration related to the net force acting on the object? So once again, our guide is going to be the student handout, but this time around, I'm going to get the student handout from the PASCO portal. You already know that I could get it from the sidebar of the teacher ebook, but this time around, just to show you that everything else is in this sidebar is in the portal and it looks different, but is still there. I'm going to go into the portal where I'm already logged in and figure out how to get this. file from investigation 5A. So back to my browser. I have a portal account. The portal is a yearly subscription where all the teachers in the school get access via that subscription. It includes experiment library, some professional learning courses, support, but what we're interested in is the curriculum. It includes full access to our PASCO Academy, all 3 subjects, and both of our textbooks, PASCO Essential Science in the form of Essential Physics and Essential Chemistry are included in this subscription. So I'm going to go to the Essential Physics tab, and all the resources that I would normally find in the sidebar at education.pasco.com in my teacher ebook, I can find via the View Chapter Resources button inside the portal. So I'll click on this, and it basically gives me a list of all the chapters. I know this is investigation 5A. Sorry, 5A. So it's going to be in chapter 5. I'll open up chapter 5, and here I can see the 6 lessons inside chapter 5. This is going to be Newton's second law, so I'll open up lesson number 4. And all of the resources that are in the sidebar of the teacher edition of the ebook are presented here: the video, the student files, and the teacher files. So I can download these. For example, I'm going to download the student work for the equipment kit I'm using today, which is the B kit. I'll download that to my computer, and I can open that up. And here is that PDF. Now, that's pretty much exactly what you could do from the sidebar of the ebook. What I just want to show you is that you also have opportunities here to do things like assign this handout to students via Google Classroom. That's built in to the portal. Or if your IT folks get the portal for your school and connect it to your LMS, you'll be able to pull in these assignments and other documents into your LMS via the portal, all the resources you see here. So we now have the student work for this investigation. I'll bring it once to the fore. And basically we're going to follow along with this and do this experiment and learn a little bit more about how to analyze data in the graph and the tools the graph makes available for doing so. So the bottom line here is we're going to look at exerting varying forces on the cart. We're going to measure those forces directly by varying the mass that's over a pulley. We'll measure the forces directly because the smart cart includes a force sensor that this hook is connected to. And we're going to look at the resulting motion of the cart, specifically acceleration, and see if we can find a pattern relating the amount of force applied to the cart and the resulting acceleration. There's a table here that we will fill out as we go through, but let's head back up here to step 1. We're going to open that Newton's second law experiment file and connect our smart cart using Bluetooth. I think we already know how to do that. But this time around, I'm going to do this in the browser. So I'm simply going to open up another browser tab. I happen to be using the Chrome browser. I could just as well be in Edge. And I'm going to go to that website for the SPARKvue PWA, or Progressive Web App, and that is sparkvue.pasco.com. I'll hit enter, and it's going to download any resources temporarily that it needs. And I'm now on the welcome screen of SPARKvue, even though this is in my browser. As always, if we're doing an essential physics experiment, we're going to start by opening PASCO experiment, going to the Essential Physics folder, and here we see the 5A Newton Second Law Lab Spark Lab. Open it just as I would if I were in the full app. And the next step we're asked to do is to connect your smart cart using Bluetooth. And it's at this point we need to pause and say this is the one place where the SPARKvue PWA differs from the app. And that's because this is inside a browser, and we have to let the browser control the Bluetooth connection. We can't let SPARKvue do it because it's in a browser. So it's fairly straightforward, but the steps are just slightly different. Thankfully, we start in the same place by opening up the Bluetooth button. But we now need to follow slightly different instructions, where we now need to launch the Bluetooth dialog of the browser by hitting this Bluetooth button. And I will turn on my smart cart. First closing SPARKvue that's already open from the prior activity. And with the smart cart turned on, I'll hit the Bluetooth button, and notice that now this is the browser that's controlling what devices are out there available to pair. Here's my smart cart. It still shows the 6-digit ID with some other data that the browser likes to show, but all I need to do is select my smart cart by its 6-digit ID, press pair, and then the browser is going to feed that into SPARKvue. And once I see my sensor show up here, everything from now on will be the same as if I was in the full SPARKvue app. So there it's connected, hit done, the start button's available, and I'm ready to go. So from now on, I will continue using the PWA, but everything is going to be the same between the PWA and the original non-PWA version of the app. All right, so we're going to set up some equipment. I have this equipment already set up on the table here. I have a level track. I will put the smart cart on it. And the key things here are we're going to add a couple of mass bars to the smart cart. This is roughly going to triple its mass. I'm going to screw the hook requested for this experiment into the force sensor. The force sensor basically has a thread here that allows us to hook various things. The cart includes 3 accessories: a hook that we're using here, a rubber bumper, and a magnetic bumper for collisions. So with that hook on, I'm going to return it to the track that I've already leveled. And the next step is, thank you. The next step is new here. It says, in your software, zero the smart cart force sensor while nothing is touching the hook. So I have nothing touching the hook there. I need to do this. And this is where I just want to remind ourselves one more time that all of these resources that are available in the portal or in the teacher ebook include supports that talk about how to set it up. These are slide excerpts again. How to zero the sensor, which I'll do in a moment. How to do the analysis. Instead of showing these slides again, I just want to reassure you those slides exist, and I'm going to be demoing it to you live here for the sake of time. So in that second step, I'm going to zero the sensor as is described here for support. I'm going to make sure there is nothing touching the hook, and then I can go to the force measurement in what we call the live data bar. By the way, it's currently reading 0.12 newtons, so it's measuring a little bit of force. It might have been configured a different way previously. I'm going to click on that readout, which is actually a button, and I'm going to choose to zero the sensor now. And now it's going to read very close to 0 force when no force is being applied. So that step is done. Now we're going to essentially put the card at the far end of the track, and we're going to connect it by a small thread to a hanger that has varying amount of mass on it. We're going to start with a 20-gram mass as described here in step 4. And we're basically going to record data where we release the cart and let it speed down the track, accelerated by this hanging mass. So let me hook the thread to the force sensor's hook. I'm going to push it down the track there and hold it since it's on the far side. And then I'm simply putting the other end of the thread over the pulley. And I have currently the 5-gram mass hanger with a 20-gram mass. And it's just out of view. Here's the mass and hanger off the end of the pulley. And I'm going to make sure that that is stationary before I begin collecting data so that it's exerting a force that's not varying with the swings. So heading back to SPARKvue again in PWA, I'm ready to start collecting data. So I'm going to press start, then I'm going to let the cart begin rolling down, and I'll press stop when the cart gets toward the end. And I think I'll ask Kane to maybe catch the cart so that it doesn't fall off the end, since my hand will be busy here in SPARKvue. All right, so press start, release the cart. Thank you. I'll press stop. All right. Thank you. So what did you get? Well, here in run number 1, we had 20 grams, and I'm going to use that scale to fit button. And we basically have 2 things we're asked to determine. One is the average net force applied to the cart during the time after it was released and before it was caught. And also, what was the acceleration during that time period? You may be looking at these graphs, force versus time on the bottom. It seems like we could get our answer to the first question out of that. Velocity versus time on the top. Well, we often show velocity because the data is usually cleaner than the acceleration data. So we're going to have to figure out how do we get a representative force from the bottom plot area, and how do we get the acceleration off of the top plot area of velocity versus time. And once again, there are slides that describe this in detail that you can use with students, but let me show you how I'm going to approach it here in SPARKvue. So first question is, what's a representative force? Well, I could go in with a tool like the coordinates tool that I previewed earlier, and I can see that the force is fairly steady as the cart is accelerating, but it jumps around a bit. I think it might be better to maybe take an average or mean of the force in this area. By the way, you can see how it changes from the tension to the applied force here by that slight drop. But I'm interested in what's the average force during the time when the cart is accelerating after being released and before being caught. So I'm going to show you a tool that we have in the toolbar. It's called Statistics, and it's represented by this Greek letter sigma. If I open up Statistics, I can choose one or more of these: minimum, maximum, mean, standard deviation, and so forth. I'm going to choose mean, at which point SPARKvue is going to look and say, well, with this entire run, the mean value is 0.138, and it just plops that right in the middle of the graph. It's important to know here, though, that I don't want the mean of the entire data set. It's artificially low because I would expect it, when I want it here, to be above 0.2, and it's clearly below that. That's because it's analyzing the entire run. So I need to figure out how to analyze just a part of the run. And the key to this is to recognize that by default, we can pan around in the graph, but we can change our cursor so that it is selecting data points, and our analyses will update to reflect the analysis of just the selected points. How do we do that? Well, there's a toggle mode down here. It toggles between move mode and select mode. I have it in move mode, which lets me push or pan the graph around. If I switch it rather to select mode, I can now draw a box. And I'd like you to notice that as data points enter this box, they get highlighted in yellow. And the analysis tool I turned on earlier, Statistics, updates to analyze only those data points that are highlighted inside the box. So I'm pretty comfortable saying that it looks like a representative force during that time period, even though there were some oscillations. I think 0.22 newtons would be a good force representing what caused the acceleration. So I can come here to the table that's inside my student handout and 0.22 newtons for that. How do I get the acceleration? Well, no matter which tool I turn on here, I'm first going to be surprised that these tools are applying to the lower plot area and not to the upper plot area. So another key thing to know about more sophisticated graphs in SPARKvue like this one is that I have two plot areas, and only one measurement of one run of one plot area is active at a time. Active means it's the one that is going to be analyzed when we turn on a tool from the toolbar. So what I need to first do is make sure the measurement in the plot area I actually want to analyze is active. And the way I can tell which measurement or run is active is by looking in the graph legend. I can see that there is a red box around the active measurement and run. Right now it's run number 1 of Y2, which is the force measurements. All I need to do is click on Y1, the velocity measurements of run number 1. That red box moves to it, and it is now the active run, meaning that I can turn on tools that apply to the top plot. When I want to determine acceleration from velocity, I think it would be nice to find maybe the slope. The slope looks very regular during this time period, the same time period that corresponds to these forces we measured. So I want to turn on a linear fit to do a linear fit to this portion of the data. So the linear fit tool has a dedicated button in the graph toolbar. And now that the right measurement is active in the legend, I'm going to turn on the linear fit. And once again, it's going to apply to the entire run. So I know how to solve that. I make sure that I'm in select mode, and then I can click and drag a box, which I can later move or adjust the size of. And now it is doing a linear fit only to those data points highlighted in yellow inside the box. And I see that the slope, which should be the acceleration, is 0.292. So let me head back here. All right. And I think you can see how we can proceed and collect multiple runs. Let me collect one more run so we can just see how the graph behaves with multiple runs. This time around, we are going to add one more mass. So we're going to have two 20-gram masses total. And we'll once again push the cart to the end of the track. Make sure that the thread with the hanger is not swinging and that it's over the pulley. All right, and I'm simply going to hit start for our second run, release it, and we'll catch it when it gets to the end, and I'll press stop. Great, thank you, Kane. All right, so I have run number 2. To keep things clean, you may notice that when I collected run number 2, run number 1 was hidden, but of course we know from the previous activity I can always make it visible. And I like to often make it visible so I can very quickly, qualitatively take a look here. It looks like run number 1 here in pink for velocity time and run number 2 in blue for velocity time. Clearly I'm getting a greater slope. And if similarly I look at the bottom, I'm getting a greater force, maybe a little bit of swinging in there, but I think my technique of doing the mean would probably work still. So let's determine the acceleration and the average force applied. for both of these in run number 2. I'm already having the velocity data active, so let me go ahead and show you that we now know I could turn on this linear fit, but we can also do this backwards. Instead of turning on the linear fit and making a selection, we could make a selection and then turn on the linear fit. And not only do I not have to go down to the toolbar, but the tools that would be appropriate for analysis here pop up, and there's the linear fit. So I find that a lot faster. Once again, instead of turning on the fit and then making a selection, we can reverse that by first making the selection and then selecting the linear fit, which pops up in an in-context tool right here. So for run number 2, that's 40 grams of mass. I'm getting a slope of 0.524. That's meters per second squared. I'll make the lower plots measurement active in the legend. I'm going to do that same trick because I can draw a box around the corresponding data, and the statistics tool appears also in the pop-up, and I can choose the mean there. And now I have 0.39 for the average force, 0.391, and this for the average, or for the acceleration. So you can see the steps, how this will proceed: changing the mass, collecting the data, typing these values into the table, or writing them down on paper if your students are using a handout. So I'm not going to belabor that. We see the mechanics of it. I'm going to open up an existing file where we have data already collected for all 5 trials. These 5 trials gradually increase the mass on the hanger from the hanger plus 20 grams to the hanger plus 5 20-gram masses. So let me close SPARKvue. Actually, I'll just open the file right here. I'm going to choose open, and I have a file that I've already collected, or I should correct that. I have a file that somebody has collected data in, and I'll explain why later because this could be useful to all of us. I'm going to open it up. I don't need to save my current file where we're just looking at the mechanics of this, and it's going to open up this file where someone has already collected 5 runs. At the same time, I'm going to open up a PDF of the assignment where we've already typed in the analysis of net force and acceleration from the first 4 trials. Let me just refresh this. SPARKvue.pasco.com. This time around, I'm opening an experiment that was saved. And right now it's on the network. That may be causing an issue. Let me try one more time. There it is. All right. So here is data collected earlier. All 5 runs are available. And if I look at my student handout here, the only thing I have left is to analyze run number 5's net force and acceleration. We'll do that the same way we've done it so far, making sure that we have a desired measurement active, then creating a selection rather, and in this case, turning on linear fit to find the acceleration, which we find to be 1.39 meters per second squared, and making this measurement active, creating a selection, finding the mean, and the force 1.01 newtons. All right, so let's proceed from there. We've collected the data from the cart. We've done the analysis to determine net force and resulting acceleration. Now it says go to the second page of the experiment file, and we're going to enter this data into another table that's inside SPARKvue. So we can have multiple pages, as we saw in the first investigation, and this one already has set up for us a table of net force and acceleration. I'm simply going to type in these values off of this table into the table in SPARKvue, and the benefit there is we're going to get a live graph of those results on the right side, and we can see overall what appears to be the relationship between net force and acceleration from the 5 trials. So typing in these forces off of the handout. And the last one is 1.01 newtons, and then the accelerations are 0.47, 0.67. And notice that we're already getting these plotted as soon as we enter the second coordinate, 0.95, 1.18, and 1.39. All right. So if we look at the graph on the right here, it looks like we're discovering a fairly linear relationship between the net force plotted on Y and the acceleration plotted on X. And as you can imagine, this lab is going to go on and ask students to perhaps do a linear fit and figure out what is the mathematical relationship between the net force on Y and the acceleration. And if I turn on a linear fit, we're going to see that the slope is about 0.728, and the lab questions have them work out that this is the units of this is kilograms. And hey, is this something close to the mass of the cart? Well, we could go measure it. And the cart is roughly 250 grams, and each of those masses is roughly 250 grams. So we can see we're beginning to get in the ballpark of the mass of the cart here, which would be 0.75. All right, so that is a quick overview of Newton's second law, where you can see the analysis has gone much deeper. And we've kind of done a meta-analysis, taking data from all of our trials and grouping it together so that we can look at the resulting net force versus acceleration across all of those trials. All right, now would be a good time to pause for a moment and say, we put a lot of work into that file, and we obviously saw that the files can be saved and reopened. That's what happened in this case. So let me talk briefly about the options we have for students to save and share data from SPARKvue files. The first option is kind of the fundamental one, and that is, can we preserve everything about the file, its displays, its data, its analyses? The answer is yes, and we do so by saving the file as a SPARKlab. SPARKlabs will have the file extension .spklab, just like Word docs are .docx. SPARKlabs are .spklab. And this can be opened later by the same person to collect more data or perform analysis, or it can be shared with anyone who has SPARKvue. And this is cross-platform compatible. So I'm going to save this from the PWA on a Windows machine. I could send it to Kane's iPhone, and they could open it in SPARKvue there. So all you need is SPARKvue, but you do need SPARKvue because this is everything about the SPARKvue file. How do we save a SPARKvue file? Well, if I go to the main menu, which is the hamburger bars in the upper left, I can choose to save this file. I'm going to choose Save As and say that this is my Newton second data. Hit save there. And now if I were to close SPARKvue, I could go back and open this file, and it would come just like I left it with all the same displays and analyses. So that's one way. It requires SPARKvue, but it preserves everything about the file. Another thing which is less popular, but is sometimes requested, is maybe you have a reason to just use SPARKvue to get data from sensors. This isn't an approach that Essential Physics uses, but you may have reason to do so. Maybe you want to get the data into a Google Sheet or Excel spreadsheet or other data analysis package. You do have the option to go to the main menu again and choose to export data. And I'm going to export this to my desktop. It's going to be exported as a CSV file, which is a comma-separated value file. And I'll go to my desktop. On my computer, CSVs are associated with Excel. So I'm going to open it in Excel. It doesn't require Excel. It's a very generic format. And I just want to note that what you get is all the measurements from all the runs from all the sensors. So I don't get any of the displays, I don't get any of the analysis. But if what I'm looking for is the raw data that was collected from all the runs and all the sensors, you'll see that that is included here. So I don't use it that often, but some teachers do that to help students to develop skills in spreadsheet analysis, or to collaborate between groups, because we could bring all of the group's data into something like Excel or Google Sheets and do some collaboration. The final thing I think is more used than exporting data, and that is I want to get my results into, say, a report that I'm creating electronically. So what I'd recommend is, in that case, take a screenshot using your operating system screenshot tools to paste into a document. Here are some popular shortcuts across Windows, Mac, and Chrome OS. On other devices like tablets and phones, it's often a double press of buttons like power and home and things like that. But I'm in Windows, so I'm going to press Windows Shift S once I have a view that I like. So I like to preserve this. I'll press Windows Shift S, and I'm going to use Windows built-in snapshot tool to get an image of my table and graph of the results. And now if I were using Word or Google Docs, I can come, and that image is in my clipboard. I could paste it in, and I could have this be the foundation of my lab report. All right. It is no longer a graph that I can manipulate, so I often save the SPARKlab, even if my goal is to get an image. But it is a way to get an image of your results into another application. So any questions about those three options for saving and sharing data from SPARKvue? Doesn't look like it. Okay. All right, please let us know as questions develop. So we have one more activity left, but before we jump into that quick activity, I want to ask you about imagine that you had some students, there was a band trip the same day you did Newton's second law, and 1 or 2 or 5 students were absent from your class. What options do you have for letting them have the experience for Newton's second law, or grading them on Newton's second law, or anything like that? Right now, what techniques do you use when you have students absent from a lab day? If you're willing to share in the chat, let us know. What would you do for students who were absent the day that the rest of the students did Newton's second law? All right, some of you may just have a grace period. You can skip 1 lab. Others of you may have been in the earlier part 1 webinar and learned the thing that I would probably think of first, and that is, Marie, thank you. Marie suggests they copy the data of 1 student. Yeah. Yep. So if they're normally in a lab group and the rest of the lab group was there, maybe that lab group could give them the data. It becomes an interesting question. At what stage should they get the data? Let's say they want to share the SPARKvue file. In a perfect world, I think they would be getting the data not with this analysis, but maybe just the raw runs, right? So that that student can still have the experience of doing the analysis and determining the force and resulting acceleration. But yeah, definitely sharing that SPARKlab file is a good idea. Let us talk about another opportunity, and that is from the PASCO Physics Academy. You'll learn in part 1 of this webinar, if you joined us, that the PASCO Academy is available, whether you're accessing it via education.pasco.com or the portal. And in the Academy, there are 25 topics, one of which happens to be Newton's second law. So I'm going to go over to the portal. I'm going to go over to the Academy. I'm going to access it via the Essential Science page. So in my correct browser here, I'm confusing myself. It's in the same browser as SPARKvue. So I'm going to go here to the Essential Science, and because I'm logged in as a teacher, I have access to the Academy. And here are the 25 topics of the Academy. I can see that Newton's second law, including investigation 5A that I just did, is here. So let me look at this and say, you know what? Those students who missed this, what do I have here? Well, this is some information about what is done in this investigation. There are some references to third-party resources. And then there are 3 videos. And these 3 videos correspond to a teacher preparation video, which could prepare you to deliver this lab in person, providing you tips and tricks, much like the video that's already included in the textbook would. But it often gives more information, like here's a demo that these experienced teachers like to do for Newton's second law. That is useful for you as kind of a professional development. What could be really useful for your absent students, though, is the middle video. This is student data collection. I'm going to launch this video, play this video here. And this video is 20 minutes long, and the goal of this video is to be the teacher's substitute when the teacher is absent because they have a sub, for example, or the student is absent because they had a field trip. So this is going to have our teachers introducing the topic to your students. In this case, they do a demonstration talking about what does net force mean, and then they jump into the actual data collection. And
the same, do you want to explain, Mr. Hanna, the setup of our system?
Talk about the setup, and then they actually go ahead and collect all 5 runs of this data, showing you how to do it, showing the students how it's done. And then they have a little handoff that says, okay, students, it's your turn. Because what also is included in the Academy with this lesson is the actual SPARKvue data file that they collected. So Marie suggested a great idea. You could copy another group's data. Well, here is a group's data, and there is a video showing its collection. So this is about the closest substitute I can think of for a student not being able to get their hands on the equipment. They can see it, and they can get the actual data file. So this data file, which can be downloaded and distributed to your students, includes the data collection, but not the analysis. The analysis is covered in the follow-up video. So you would probably cover analysis with your students, but let's say they were absent for a week. There's another video in which our teachers speak as instructors to do the analysis with your students, including walking through the analysis in SPARKvue and answering the questions prompted by the handout. So I think the most useful file for many teachers here is let us show your students or you, the teacher, for an orientation, what this lab looks like. Let us collect the data and give you the file that we collected so that you can continue with the data analysis and interpretation. All right, so one opportunity to use the resources of the Physics Academy. Once again, the Physics Academy is available, as I just did, via education.pasco.com with a teacher login, or via the portal where all three academies, physics, chemistry, and biology, are all open to all subscribers of the Academy. So we have just under 20 minutes left. We are going to switch gears now and continue doing a sensor lab, but it's going to be a lab without the smart cart that we've been using so far, so that we can introduce you to another set of sensors. This investigation, I'm not going to jump into the resources available. We know those resources and we've seen them, where we can get them both at education.pasco.com and in the portal. So we just know those resources exist. In this case, I'm just going to walk you through this lab very quickly so we can learn about the hardware and sensors used in it. All right, so this lab starts by telling students, you know what, students, in the handout, go ahead and construct the following circuit. And the way that they are going to construct that circuit is to use the modular circuits kit. The modular circuits kit is one of those kits included in the standard bundle. And the design goal of modular circuits, as you can see here on the video feed, is to allow students to replicate the circuits. So it allows a one-to-one correspondence of what does the circuit look like in its schematic representation and what does it look like on the tabletop. So here's a graphic representation of what I'm about to build and have already partly built in the live video feed. So we have the main components here. We have a battery at the bottom. We have a switch that's currently open. We have a current sensor. Now, this doesn't look like our standard sensors. The smart card is a sensor. It's also not a standard sensor, but most of our wireless sensors look like this. This is a voltage sensor. It's a white box. The modular circuits kit comes with the EP3 modular circuits kit comes with a wireless current module, and it's very intentionally designed to look and act like a module in this modular circuits kit, because we want to put this, and we want to break the circuit when we measure current. So this enforces that concept of how we measure current. We open up what would normally be the circuit that might have started like this, and we insert the current measuring device in there. So these blocks are the components, the modular components of modular circuits. We connect them physically, and then we also need to connect them electrically with these little pins that are included. So I'm going to reconnect electrically the current sensor module that's in there. And this lab is asking us to look at the current that passes through particular resistors. The modular circuits includes resistor modules. We're going to begin with a 10 ohm resistor module, which I'll place here at the top of the circuit as you're looking at it. And I'll be sure to clip it in so that we are looking at an electric circuit that is currently closed except for the switch that remains open so we don't waste the battery. All right, and of course all these instructions and background are provided in the resources available in the Teacher Edition. So what are we going to do in this activity? Well, we're going to open up a file in SPARKvue as we always do. This time around I'll return to the SPARKvue app. Go to Open PASCO Experiment, and this in the Essential Physics folder is Investigation 17C, Resistance and Ohm's Law. And the lab is going to basically have us just monitor the current as we change the resistor value and see for a single battery, what is the corresponding current through the circuit. So we're going to connect our current module. It is yet another sensor, so there's a power switch on it. And nice thing about these circuits is you can also lift them up and hold them up. I've turned on the power to our wireless current module. It's blinking red in its Bluetooth light. So it shows up here. It still has that 6-digit ID. It is just a sensor. And I'm going to connect to it wirelessly. And once I do, it's going to show up here in the wired connected devices list rather, and its light will begin blinking green. So I now should be able to measure the current, and I'm going to measure the current here by hitting start, closing the circuit, and I can see that for a 10 ohm resistor, I get 0.143 amps. All right. So I would write that down, of course, in the table that's provided in the handout. Show you what that looks like. So we're recording the current and the resistor values for about 5 resistors. I'll do one more, actually I'll do 2 more swaps. Here is a 33 ohm resistor module that's included in modular circuits. So I'll pull out the 10 ohm, insert the 33 ohm, wire it back up with these clips, close the switch temporarily, and I can see I get 0.046 amps for 33 ohms, and recording this in the table will continue. Things get a little more interesting when we finally get to the 100 has a module, but past that we kind of need to improvise, and the way we can do that is that we have a spring clip module, and the spring clip module will let us put components here. I have a 330 ohm resistor here, so I can put that module in, wire it back up, close the circuit, and see that the current gets quite small in that case. 330 ohm resistor gives me 0.004 amps. All right, so you can see how this first part of the lab proceeds. We're gathering related pairs of the current through the circuit with a one battery and the nominal resistance of the resistor we have in there. All right, so the lab continues then to ask us to determine the inverse current, the inverse resistance, so 1 over R. And although this handout doesn't tell students to do so, this file, this configuration file, once again is configured so that we can do this more directly. There is a page here that, like the Newton's second law page, lets us type in the currents and type in the corresponding resistances. And once again, let me see what we can do here with an existing file so we don't have to belabor the actual data collection. And for the sake of time, let me show you what I did to actually get the Newton's second law data. We know that a data file was collected for this in the PASCO Academy. So I'm going to jump over to the Academy, go back to the topics, and find the Ohm's Law lab right here, circuits and resistance. And here's the lab collected data. Open that up in SPARKvue, so I close SPARKvue here. And as an instructor, this is a great way to see what the data might look like and do your own analysis if you're, say, doing it from home and don't have the equipment on hand, or just don't have the time. All right, so here are, I believe the video actually has the current shown on the screen, so it's up to students to write it, but typically these files would include the data there. So we type in the current, we'd have the resistance, it would be plotted one against the other, and we would see an inverse relationship. So far, we have not looked at relationships that weren't linear in the graph, but there are curve fits that support inverse relationships. Under this linear fit, we have only a linear fit, but there is a general curve fit button next to it that allows us to look at linear again and other relationships, including the inverse fit that we would expect when we're looking at the relationship between current and resistance. All right, I think I probably have enough time here to actually collect this data. I'm sorry, I don't have the data file here. Any questions as I jump through that? I'll very quickly get some values here. Serves as a reminder to always save my files. So I'm going to reconnect to the current sensor. And let's get at least the first 4 values here so I can show you in actual detail what the nonlinear curve fit looks like. All right, so first we have 10 ohms, and that is 0.147. 148. All right, and I'll switch over to 33. 0.46. And I think we'll begin to see the nonlinearity with just the next value, which is 100 ohms. see a smaller current, right? Close the switch, 015. And I do have in the spring clip module a 330 ohm resistor, which happens to match the one that the video used. So just do 4. This is 0.004 amps. So it's getting quite small at that point. All right, and we won't use that one. So thanks for your patience. We can see on the graph here, if we unlock it and scale to fit, that we clearly don't have a linear relationship. Again, this is current on the y-axis and resistance on the x-axis. But if we go into our non-linear fits, we could take a look at various ones, inverse, square, and need to make sure I'm looking at the right run here. So with run number 4 active, I'll turn on the inverse fit, and looks like it does pretty well with the 4 data points that we have found. So I think we found evidence of an inverse relationship between current and resistance. By the way, if you are distracted or your students are distracted by those straight connecting lines, one of the graph settings available in the settings gear is to turn off the connecting lines. So that makes it a little clearer that we're not looking at the segments in between, but rather looking at this inverse relationship across the data points. This lab handout continues to ask students to now calculate 1 over the resistance so that they can linearize the graph, but we are already confident we can get to that because we have an inverse fit here. So that's an example of a modular circuits experiment. That's part 1. Part 2 continues and introduces another key sensor in the modular circuits kit, and that is the wireless voltage sensor. So if part 1 has students confirming V equals IR, or Ohm's law, part 2 asks them to add the wireless voltage sensor and essentially to use a component with an unknown resistance. It happens to be the light bulb that's included. We, as physics folks, know that the resistance of a light bulb can vary. It's non-ohmic, but it will have a particular resistance at a particular temperature. And if I open and close this, you may not be able to see, but it does light up. This lab asks students to recognize that we've discovered Ohm's law, and we can now use the fact that if we have a circuit element or a bunch of circuit elements, let's say a light bulb, whose resistance is unknown, if we know the current through it and the voltage across it, we can use those 2 facts in Ohm's law to determine what the resistance must be. So in this file, I will add to it a wireless voltage sensor by clicking on the Bluetooth button. My current sensor remains connected. I can add the voltage sensor. And we're going to measure both the voltage and current, where it's the current through the circuit and the voltage across the light bulb. And from this, students will be asked to use Ohm's law to determine what the present value of the resistance of the light bulb is. So let me hit start. I'll go ahead and close the circuit. And we can see that the light bulb is lit up. We have a current of 0.05 volts and a voltage drop of 1.54 volts. So we could use Ohm's law to figure out what the current resistance of that light bulb is. So that is the investigation, resistance, and Ohm's law. Kane, any questions coming in? Nope, looks good. All right. So that's the third and final activity today. Hopefully this has given you a view on how we can use the resources from the teacher ebook or in the portal to support our students' performance of hands-on investigations that use the PASCO sensors and SPARKvue software. If you wanted just one thing to summarize what we've done today and to review it, I'd point you to the following video guide. It's available on education.pasco.com. It's also in the portal. I'll show you where it is on education.pasco.com. If we go to our main page for education.pasco.com and scroll down, there are a number of videos that talk about the textbooks that were covered in part 1, but we have this one called Using SPARKvue Software. And in this 6-minute video,
Hi, welcome to the video guide to using SPARKvue software with Essential Physics 3rd edition.
we go through and introduce all of the tools that are used for data analysis across all of the experiments in essential physics that use SPARKvue. So this is kind of a synopsis of all the tools. We've covered a lot of them today. We've looked at linear fits, nonlinear fits. We have entered data into the table. In a prior part 1, we looked at the FFT in the SPARKvue software, and we've looked at area and selections. All of those tools are covered in 6 minutes. So this is a great resource for both you and students to give you a sense of what do you need to know about SPARKvue to do the activities across the entire book that employ SPARKvue and sensors. The other thing I'll note is that if you want to go even farther than we've gone in parts 1 and 2 of these webinars, if you have a subscription, that is, if your school has a subscription to the PASCO portal, we have a full multi-hour self-paced course called Essential Physics 3rd Edition with Equipment. This covers both the SPARKvue side of things and the textbook side of the Essential Physics program. And once you finish it and pass all of the quizzes that are provided there, you'll earn a certificate showing that you've learned quite a bit about the Essential Physics program. So before we wrap it up here, I just want to invite you, if you have further questions, to contact your regional PASCO representative. This URL, pasco.com/support, will bring you to a page where you can find your representative across the US and in countries around the world, and also get in touch with other PASCO parties like tech support if you have particular questions about the implementation of these or how to get things hooked up with your IT folks, installing software and so forth. So with that, I want to stop the recording and thank you for joining us today.